Okay, now we will see. Already we have seen what is meant by electric potential and potential difference. What is potential difference? The work done in bringing a unit positive charge from one point to another point against the electric force, that we call it as potential difference. What is electric potential? Same way I can define this electric potential as the work done in bringing a unit positive charge from infinity to a point against the electric force. We call it as electric potential. Now I have two charges, 2-point charges Q1 and Q2. If I have 2-point charges Q1 and Q2, how to find out this electrostatic potential energy of the system of charges? That we will see now. We already seen what is meant by potential difference and electric potential. Now we will see how to find out the electrostatic potential energy for a system of charges. Here I have 2-point charges Q1 and Q2. Let these 2-point charges be at the point A and B. Now at the point QB, that is Q2, I have a point charge Q2. The work done in bringing this charge Q1 to this point Q2, to this charge Q2, which is separated by distance R. That potential at this point B is given by, we know that the potential, electric potential due to a point charge is given by the formula V equal to Q by 4 pi epsilon naught R. Here at the point B, what is that electric potential in bringing that charge Q1 to this charge Q2? It is given by V equal to Q1 by 4 pi epsilon naught R. Now here at this point, this much of potential we have. So V equal to Q by 4 pi epsilon naught R. Now you bring another charge Q2 from infinity to this point. So what I am going to do here? I am going to bring another charge Q2 from infinity to this point Q2. It is at the point B. Now the work done in bringing the charge Q2 from infinity to this point B is given by the formula that work done will be stored as electrostatic potential energy in the system of charges Q1 and Q2. So W equal to V into Q2, because I was bringing the charge Q2 from infinity to this point B. So we know that what is the potential at the point B? This is given by, so what is V equal to Q1 by 4 pi epsilon naught R? This is nothing but the potential at the point B. So I can write this work done is equal to Q1 by 4 pi epsilon naught R into the charge Q2. So this work done will be stored in the system as electrostatic potential energy. The symbol for that is U. So U equal to Q1 Q2 by 4 pi epsilon naught R. So in this way I can define this electrostatic potential energy U equal to Q1 Q2 by 4 pi epsilon naught R. Same way I can also find out what is the electrostatic potential energy at this point A. You will be getting the same formula only. Here also you will first find out what is the potential at the point A. Then you just find out what is the work done in bringing another charge Q1 from infinity to this point. Then also I will be getting the same formula U equal to Q1 Q2 by 4 pi epsilon naught R. So we know that V, what is V here? Electric potential due to a point charge. For that what is the formula? Q by 4 pi epsilon naught R. This is the electric potential due to a point charge. This is electrostatic potential energy due to a system of charges. Here I have only 2 charges. We may have any number of charges. For example, I have 3 charges which are placed at the vertices of a triangle. So in the system of charges, I want to find out what is the electrostatic potential energy. In that example, I have only 2 charges. That is a system. In that system of charges, I just find out what is the electrostatic potential energy. So how I can define electrostatic potential energy? It is nothing but the work done in bringing the charge from one point to another point, from infinity to this point, or simply I can say what is the work done in assembling the charges in the system. What is the work done in assembling the charges in this is the system? We call it as electrostatic potential energy. Now, here I have three charges Q1, Q2, Q3, which are at the three vertices of a triangle. Let the distance of separation between any two charges, let this R1, R3 be the distance between the two charges Q1 and Q2. Then R23 be the distance of separation between Q2 and Q3, and R12 is the distance of separation between the charges Q1 and Q2. Now, I want to find out what is the electrostatic potential energy in the system of charges which are placed at the three vertices of a triangle. So, U. How to find out the total potential energy? First, I'll find out for these two charges, for these 2 point charges, U23 be the electrostatic potential energy. Same way, you find out for these two charges, Q1 and Q2, and for Q1 and Q3. So, what is U23 electrostatic potential energy for these two charges? What is U12 electrostatic potential energy for these two charges? Same way, U13 is the electrostatic potential energy for these three charges. If you add all these three electrostatic potential energy, I will be getting total electrostatic potential energy of the system of charges. So, I can write this as U12 plus U13 plus U23. So, one example I have seen with only 2 pointers. Here I have 3 point charges which are at the three vertices of a triangle. How I can write this? We know that what is the electrostatic potential energy formula? U equal to Q1 Q2 by 4 pi epsilon naught R. Don't forget this. Then what is V? Electric potential due to a point charge. It is given by Q by 4 pi epsilon naught R. Now, U12. How I can write this U12 just for these two? Can I write like this? Q1 Q2 by 4 pi epsilon naught. The distance of separation between these two charges is R12 plus next one is U13. That is the potential energy. It is given by Q13 by 4 pi epsilon naught R13 plus for this U23. This Q2 Q3 by 4 pi epsilon naught R23. Now, on all this, can I take this 1 by 4 pi epsilon naught out? Isn't it? So, what is the remaining? Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. So, this gives you the electrostatic potential energy for this system of charges. So, what we see now? These two are very important. What is here? Electric potential due to a point charge. This one is electric potential energy, electrostatic potential energy for a system of charges. That is for a point charge. This is for a system of charges. For if they have n number of charges also, I can easily find out this electrostatic potential energy stored in a system. Now, we have seen the, can you say the Coulomb's law, the formula, final formula F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Same way. What is E? Electric field intensity is given by 1 by 4 pi epsilon naught Q by R square. So, all these three formulas are very important in this chapter. Now, we know what is meant by electric dipole. Can you say some examples for electric dipoles? Already we have seen what is an electric dipole? Two equal and opposite charges separated by a very small distance constitute an electric dipole. What are the examples given in your reader for electric dipole? Is water, ammonia, water, ammonia, then carbon dioxide, chloroform. So all these are very good examples of electric dipoles. That means all these molecules, the centers of gravity of the positive and negative charges are separated by a very small distance. That is why these are taken as very good examples for electric dipole. Now, if I say a dipole, we will be having two charges, one at a point, another at a point. Let this charge be minus q and let this charge be plus. These two charges are equal in magnitude, but they are opposite. That is, this one is positive charge, this one is negative charge. They are separated by distance of 2. What is 2d? Distance of separation between these two charges. This constitutes a dipole. Now, what happens when a dipole is placed in a uniform electric field? If I draw parallel lines of force, this shows this electric field as uniform electric field. If I draw lines like this which are not parallel to each other, this shows this electric field as not uniform electric field. Now, we are going to see what happens when a dipole is placed in a uniform electric field. I am going to place a dipole. Let E be the electric field intensity of this uniform electric field. Here, let A, B be the electric dipole. Let 2 be the distance of separation between the two charges, minus q at A and plus q at B. Now, so where it is kept? It is kept in a uniform electric field. So, here these two charges will be experiencing a force since it is kept in a uniform electric field. So, this charge will experience a force which is given by F equal to QE. How I got this formula? We know that E equal to this one. What is electric field intensity? Force experienced by unit positive charge. Force exerted on a unit positive charge, we call it as electric field intensity. So, E equal to F by Q. What is F from this formula? F equal to QE. So, this much of force, this charge will be experienced when it is placed in a uniform electric field. So, let F equal to QE. Here, the same way, this charge will also experience some force since it is placed in an electric field of intensity E. So, let this force experienced by this charge minus Q be F equal to minus QE. If you see the magnitude of these two forces, they will be equal in magnitude, but they act in opposite direction. That is, one force due to the charge plus Q will be acting in this direction. Another force due to the charge minus Q will be acting in the opposite direction, but these two will be equal in magnitude. So, these two are unlike parallel force. They are parallel forces, but they are acting in the opposite direction. So, unlike parallel forces, they constitute the turning effect. Because of this force, what force it is exerted? It is exerted by an electric force. So, these two forces are equal in magnitude. So, what happens to the net force? Can you see? What happens to the net force on these two charges since it is placed in a uniform electric field? I told you already these two forces are equal in magnitude. They act in opposite directions, so they cancel each other. What happens to the net force? It is 0. Then, since these two forces act in opposite direction, what is the net force? It is 0. Because of this, what happens to the dipole? It will be turned through a certain angle. That is, it tends to align the dipole in the direction of the electric field. So, there will be a torque effect. There will be a turning effect because of the uniform electric. So, the dipole will turn through a certain angle. Let that be theta. Now, how to measure this magnitude of this charge? It is given by the formula. Charge now equal to one of the forces into the perpendicular distance between them. What is the perpendicular distance? You produce this backward. Same way here also. So let this be C. This point is A. Always in a dipole, we will have minus Q at A and plus Q at B. So always be positive. Remember like that. B positive. A minus. So this is the perpendicular distance. Which one? BC is the perpendicular distance. So I can write this as F into BC. Torque tau equal to, torque is the effect, turning effect experienced for this dipole since it is placed in a uniform electric field. You are going to find out the magnitude of this torque. F, we know that. What is F? These two charges will have the same force. So I can write F equal to QE. I want to find out what is the perpendicular distance BC. In this triangle, I can find out what is BC. So here I can write BC as sine, the opposite side. So sine theta equals to, from this right angle triangle, can you find out what is sine theta? Sine theta formula is opposite side by hypotenuse. What is opposite side? BC by hypotenuse. What is hypotenuse here? AB. Nothing but your length of the dipole. That is 2D. From this, what is BC? This 2D sine theta. So in the place of BC, I can write 2D sine theta. So torque tau equal to, you can also rewrite this equation as 2D Q into 2D E sine theta. Here, this Q into 2D is nothing but your dipole moment. So what is the dipole moment? How to measure this electric dipole? It is measured by electric dipole moment. Nothing but product of one of the charges into the distance. So I can write this torque tau equal to E sine theta. So this is the torque effect when a electric dipole is placed in a uniform electric. So we have calculated what happens when a electric dipole is placed in a uniform electric field. We will go for the special cases in this. Now, when a dipole placed in uniform electric field of intensity, what happens to the net force? Net force is 0. What will be the torque? It is given by PE sine theta. This we have seen now. Here the dipole is placed in a uniform electric field. Net force is 0 and the torque is PE sine theta. I can write this in vector form as tau vector equal to P vector cross P vector. Now, go for the second condition 2. If this dipole aligns parallel to the direction of the electric field. So this is the electric field direction. Now the dipole is like this. What happens if the dipole aligns parallel to the direction of the electric field? What happens to theta? Theta equal to 0. Then sine 0 is 0. So it will be having no torque at all. So in a dipole aligned parallel to the electric field, it will be having neither a force nor a torque. Now, what happens when this dipole perpendicular when this to the direction of the magnetic electric field? When this dipole, this is the direction of the electric field. Now the dipole is like this, AB. So what happens to the theta? It is 90 degrees. When the dipole is perpendicular to the direction of the electric field, theta is 90 degrees. Then sin 90 is 1. So tau equal to PE. So it will be having maximum torque when it is aligned perpendicular to the direction of the magnetic field. Torque is maximum when theta is 90 degrees. So these are the cases when we can see what happens to the torque when it is aligned parallel to the electric field, when it is aligned perpendicular to the electric field. All these are in a uniform electric Now, when the torque is maximum, when it is aligned perpendicular to the electric field, that is theta is 3. Now, what happens when a dipole is placed in a non-uniform electric field? Now, I am going to place a dipole in a non-uniform electric field. What happens when a dipole is placed in a non-uniform electric field? This electric field is like this. Here I place a, I am going to have an electric dipole. A, B, here plus Q, here minus. So, what happens when an electric dipole is placed in a non-uniform electric field? It experiences both a net force and a torque. What happens? It will be having net force and also torque. So, these are the very important conditions you want to notice when you are dealing with the torque. That is, when a dipole is placed in a uniform electric field, net force is 0. Torque is this much value. When it is placed in a non-uniform electric field, since it is non-uniform, it will be having both net force and torque. In a uniform electric field, when the dipole aligns parallel to the field, torque is 0. Neither a force nor a torque it will be having. When it is placed perpendicular to the direction of the magnetic field, electric field, it has 90 degrees. So, torque is maximum, that is tau equal to 3E. Now, when a dipole is aligned or it is placed in a uniform electric field, what is actually happening? The dipole tends to align itself. That is, some amount of work is done in turning the dipole to a certain angle theta, isn't it? So, initially the dipole it will be like this. Since because of the effect of this electric field, it turns through an angle theta, isn't it? So, some amount of work is done in turning the dipole to a certain angle theta. That work done is stored in the dipole in the form of potential energy. You are going to see how will be the potential energy for a dipole. That is nothing but the work done in turning the dipole to a desired position. Now, same example. So, this is the dipole A. Always we will be having minus Q at A. B at B we will have plus Q. So, here at E be the uniform electric field. These two charges will be experience a force that is given by F equal to QE and here F equal to minus QE. Distance of separation is 2D. So, because of this electric field, let it makes an angle theta. So, how much angle it has turned? Let theta be the angle up to the at which that is it is turned to an angle theta because of the electric field. Now, what's our work? I want to find out what is the total work done in turning the dipole to a certain angle theta. That work done will be stored in the form of potential energy. First, we know that what is the force experience? That is the torque is also a force. What is the force experienced by a dipole when it is placed in a uniform electric field? It is given by CE sin theta. Already we know that net force is 0. Clear? Now, first we will calculate what happens when it is turned to a small angle d theta. First we will calculate what happens when the dipole is turned to a small angle d theta. Let that work done be dW. So, dW equal to work done equal to force into displacement. By that formula I can write dW equal, what is the force experience here? Tau. Tau into d theta. So, this is a small amount of work done turning the dipole to a certain angle d theta. I can find out the total work done in turning the dipole to angle theta. I can integrate this dW. If I integrate this small amount of work done, I will get the total work done. So, W equal to integration of dW. dW is nothing but tau d theta. What is tau here? The torque is given by CE sin theta d theta. P is your electric dipole moment. E is electric field intensity. These two are constant. So, you please take it out. So, work done W equal to PE integration of sin theta d theta. What is integration of sin theta? this is, so integrate sin theta, it will come, what you will be getting? Minus cos theta. So this work done is W equal to minus PE cos theta. This work done will be stored in the form of potential energy. So I can write this U equal to minus PE cos theta. So what is here U? It is nothing but the potential energy that we are work done in turning the dipole through a certain angle theta. Now, what happens when the dipole is aligned parallel to the field? Can you say? Already we have seen the case. So for the previous case, we have seen this. Now, what happens when the dipole is aligned with the field? Now, the dipole is like this, AB. What is the angle between this electric field and the dipole? 0 degree. So, cos 0 is 1. Cos 0 is 1. So, what happens to the potential energy when the dipole is aligned parallel to the field? Now, the dipole is aligned parallel to the field. So, theta equal to 0 degree, cos 0 is 1. So, the potential energy is minus Pt. So, it has minimum potential energy when it is aligned parallel to the field. This is the important one mark question. So, when the dipole is aligned parallel to the field, potential energy is minimum. So, whenever the dipole made to align to the field direction, some of its potential energy will be wasted in the form of heat to the surrounding. So, what happens when a dipole aligns, that is this electric field, because of this electric force only, this dipole tends to align in the direction of the electric field, because this force will be making it to rotate. So, this electric field, when it makes the dipole to align in the field direction, some of its potential energy will be wasted, that is dissipated in the form of heat to the surrounding. This heat, this principle we are going to use in our day-to-day life. Can you say example for this? A very good example. So, what I told you, when the dipole aligns or tends to align in the field direction, its potential energy will be wasted in the form of heat to the surrounding. Where we are going to use this principle? Can anyone say? Adane heat vandu potential energy heat adukku waste aayidhu to the surrounding. To the surroundings pogra heat I can use it for my practical purpose. Where we are going to use this? We heard about the microwave oven. This principle we are going to use in the working of a microwave oven. What for we will use this microwave oven? To cook the food in a short time. So, it is easy to cook the food when I use the microwave oven. In a short time I can easily cook the food. So, here what happens when I cook the food in a microwave oven? Step by step you will see. So, what you will do to cook any food. For example, I will give you potato. You want to cook that potato. What you will do? Take a dish, microwave oven dish, pour some water, clean the potatoes, cut it into pieces and you will put it, isn't it? So, you will add water. Without water, it won't cook. So, what you will do obviously, you will pour some water, then you add that vegetables what you want to cook, then you keep it inside the microwave oven. So, what is the first step you will do in the working of a microwave oven? You will switch on. When you switch on the microwave oven, what happens? Microwaves are generated. So, here when the microwaves are generated, we are having the water here. Here I have my vegetable, whatever it may be. I kept it in the microwave oven, isn't it? So, this microwave generator will produce non-uniform, this is very important, oscillating electric field. So, what type of electric field these microwaves will generate? When the microwave is switched on, it produces a non-uniform oscillating electric field. So, already we know that this water is in the beginning itself I told you Examples for dipole. Water is the water molecules are very good. Electric dipole. Water molecules act as electric dipole. Now imagine this electric dipole is placed in a non-uniform electric field. Just now we have seen when a dipole is placed in a non-uniform electric field, what happens? It experiences both a net force. Net force then it will be having torque also. Both it will be having. Clear? Now the water molecules which are very good electric dipole are kept in a non-uniform electric field. So first point, it produces non-uniform oscillating electric field. Second point, the water molecule will act as electric dipole. Electric dipole. So what happens? Because of this non-uniform oscillating electric field, this electric dipole, that is the water molecule, gets excited. So what they will do? They will experience the torque effect. What type of torque effect they will be experience? They will have a oscillating torque. So what is the effect now? Because of the non-uniform electric field, this water molecules which are a very good electric dipole or act as electric dipole, they will be getting a oscillating torque. We know that when a electric dipole tends to align itself in the direction of the field direction, its potential energy will be dissipated in the form of heat to the surroundings. So because of this, some bonds will be broken since it is having an oscillating torque. Some bonds that are broken and it really produces heat to the surroundings. This heat which is given to the surroundings is used to cook the food in a charge. So this principle, what we have seen so far, we are using in the working of a microwave. So what is the first step? In the microwave oven is switched on, microwaves are generated, which in turn produces a non-uniform oscillating electric field. This water molecules which are very good electric dipole will have a oscillating torque. Because of this oscillating torque, this water molecules get excited and its bonds are broken. When the bonds are broken, heat energy is released. That heat energy we are going to use to cook the food in a short time. So these three steps are very, very important. The important application oriented 3-mark question. So we have seen what happens when a dipole is placed in a uniform electric field. What is the torque effect and what happens when it is placed in a non-uniform electric field and what is its potential energy and its application. This is in the working of a microwave oven. Already we have seen what is the electric field due to a dipole at a point on its axial line. What is the electric field due to a dipole at a point on its axial line and at a point on its equatorial line? What is the electric field? 2p by 4 pi epsilon naught r cube. Can you remember? Already we have seen the derivation for these two. Electric field due to a dipole at a point on its axial line. Just given by the equation formula 2p by 4 pi epsilon naught r cube. Then what is the electric field due to a dipole at a point on its equatorial line? This is given by p by 4 pi epsilon naught r cube. So which is greater? Which is greater? E axial. It is twice that of the E equatorial. So this and all already we have seen. Now we will see what happens to this electric potential due to a dipole and on its axial line and also on its equatorial line. So this we are going to see now. So that is, we are going to find out its electric potential. What happens to the electric potential due to a dipole at any point? First we will calculate the electric potential due to a dipole at any point. Then we will find out what happens to the electric potential at its axial line and on its equatorial line. Draw the diagram now. Always when I draw the dipole, I will have always minus q at A and B. At B I have stress. Let O be the center of the dipole. Now going to have a point. It is not on the axial line. It is not on the axial line. At any point. So let the point be here. We join this point to the center of the dipole. Point is here. You should not draw exactly on the equatorial line. It should be slant. Join these two. Here I have. Cannot produce this. Then you join this. Yeah. Now we know that the distance of separation between the two charges is given by 2d. Then this one is d. Half of 2d is d, and this is also d. Let this point P is at a distance of r from the center of the dipole. Now observe what I want to find out. What is the electric potential at this point P due to this dipole P? We will see one by one. Now, at the point B, due to the charge plus Q, I will find out what is the electric potential. Similarly, at the point A, due to the charge minus Q, I will find out what is the electric potential. We know that what is the electric potential due to a point charge is given by V equal to Q by 4 pi epsilon naught R. So this is the electric potential due to a point charge. First, let V1 be the electric potential due to the point charge plus, which is given by Q by 4 pi epsilon naught. The distance between B and the point P, I will take it as R1. And the distance between A and the point P, I will take it as R2. Now here, it will become R1. Let this be equation 1. Now, similarly, I can find out what happens to the electric potential due to the charge minus Q at A. It is given by minus Q by 4 pi epsilon naught R2. Let this be our equation 2. So, we have found out separately due to the what is the electric potential due to the 2 point charges plus Q and minus Q placed at B and A respectively. I want to find out the total electric potential due to this dipole. Because of the dipole, what is the total electric potential? This is given by V equal to V1 plus V2. Is given by Q by, so in these two formulas, Q by 4 pi epsilon naught is come. Just take it out. Q by 4 pi epsilon naught. What is the remaining? 1 by R1 plus minus. It will become plus into minus. It will become minus 1 by R. So, the total potential due to the dipole at any point is given by V equal to Q by 4 pi epsilon naught 1 into 1 by R1 minus 1 by R2. Now, our work is to find out this R1 and R2, that is 1 by R1 and 1 by R2. We will go 1 by 1 first. How to find out this 1 by R1? So, to find out, first I will take this R1 for this triangle OPP. In this triangle OPP, we know that R1 square is equal to R. This is R1. R1 square is equal to R square plus D square minus 2RD cos theta. So what happens? We know that R1 square is equal to R square plus D square minus 2RD cos theta. In the I will take R square to be common. If I just take R square out, here it will become 1 plus. Here I don't have the term R square. So what happens to this? D square by R square minus, already I have R in here. So here I have taken R square. So what happens now? 2D cos theta by R. Since I have only one R, divided by I got that. Now, when this R, that is the point P, is far away from the dipole, I can neglect this D when compared to R. See here, this D is very, very less. This distance D is very less when compared to R. In this case, I can neglect this D square by R square. So here, when d is very less than r, d square by r square can be neglected. Why? Because compared to this r value, this d is very less. So, I can neglect this d square by r square. So, this will be removed. So, what happens to this r1 square? This is equal to r square into 1 minus 2d cos theta by r. What's our work? I want to find out 1 by r1. So, here, what is r1 now? Can take the square root. If we want r1 equal to r into 1 minus 2d cos theta by r. Root I can write it as 1 by 2. So, I have calculated what is r1. From this, what is 1 by r1? 1 by r1 equal to 1 by r into 1 minus 2d cos theta by r. Since it is a reciprocal, I can write it as minus of. Now, using binomial expansion, I can expand this 1 minus 2d cos theta by r. We all know what is binomial expansion formula. Please make a note of that. 1 plus x whole power n equal to, say the formula, 1 plus nx by 1 factorial into 1 plus n into n minus 1 by 2 factorial x square plus n into n minus 1 n minus 2 by 3 factorial x cube. That will be going on. So, this is your binomial expansion. Now, I am going to expand this term using binomial expansion formula. Binomial expansion. Now, in this binomial expansion, this term 2d cos theta by r is very less. Here, d is very less. Then I am going to divide this with a higher value. So, I will get only a lesser value. In this binomial expansion formula, if this x value is very small, how I can write this formula? Provided, this is the condition. In this binomial expansion, if this x value is very small, I can neglect the term of higher power. What I can do, if this x value is very small, I can neglect the term with higher power. So, these are the higher powers. These can be neglected when this x is very small. So, what happens to this formula? 1 plus x whole power n, it will become 1 plus nx. If it is 1 plus x, 1 minus x whole power n, under the same condition, it will become 1 minus n. Then, if it is 1 plus x whole power minus n, it will become 1 minus n. If it is 1 minus x whole power minus n, it will become 1 plus n. So, these are very important. Make a note of it. These 4 formulas you are going to use here. Now, this term, that is, this is nothing but your 1 minus x whole power minus n. So, it is of the form 1 minus x whole power minus n, it is equal to 1 plus nx. Here, this value is very less, so I can neglect the term with higher power. So, using binomial expansion and neglecting the higher power, this is an important 10-mark question, and neglecting the higher power, what happens to this 1 by r1? Please note this 1 by r1 will be equal to 1 by r into 1 minus nx. So, 1 plus nx, 1 plus, what is n value here? This is x and this is n. What is n now? N is your 1 by 2, isn't it? The power. Because the formula is 1 minus x, 1 minus x whole power minus n is 1 plus n. I have written as 1 by 2. Here, this value is your x value into 2d cos theta by r. 2 gets cancelled. Then, what is the remaining? 1 by r1 equal to 1 by r into 1 plus d cos theta by r. So, I have calculated 1 by r1 using this. So, how you are calculating 1 by r1? First step, you want to find out what is the r1 square. You write that formula. From that r1 square, you find out what is r1. Take the square root. Then in that r1, you just neglect the d square by r square, because when compared to r, d is less. So, you neglect the d square by r square. You finally calculate what is r1. Then check the value. So, you find out what is 1 by r1. It will become the power minus r. Then only at last you are going to expand this term using binomial expansion. Finally, I will be getting 1 by r1 equal to 1 by r into 1 plus d cos theta by this is your second. Now, similarly, can I find out what is 1 by r2? Shall we go for that? Please note down all these formulas. Similarly, I can also calculate what is r2 square. So, if you look at the diagram, the point P is here. We have joined this A and B. This angle, this is B, this is A, here it is minus Q, here it is plus. Now, plus Q to minus Q is a dipole moment. Here, this angle is theta. This angle I have taken it as theta. Then what is this angle? The total angle is 180 degree. Now, this is 180 theta. This angle I have taken it as theta. So, what happens to this angle now? 180 degree minus theta. I don't know what is theta. So, here it is r1. This one we have calculated. Now, I want to find out what is r2. Similarly, I can write this r2 square as r1 r2 square plus d square minus 2rd cos is 180 minus theta. It is not cos theta. For this r2 is cos 180 minus theta. What is cos 180 minus theta? Say fast. What is r cos 180 minus theta is r2 square plus d square cos 180 minus theta is minus cos theta. Take down this. Cos 180 minus theta is minus cos theta. So, I can write this as minus 2rd cos theta. Minus into minus, it will become plus d square plus 2rd cos theta. So, r2 square is equal to r2 square plus d square, or it is where we are taking this r2 r. Now, same way I can write this. If I take r square out, so what happens to this? 1 plus d square by r square plus 2d cos theta. Similarly, how you did for calculating 1 by r1? Similar steps we are going to follow. The only difference is here it is not cos theta, it is cos 180 minus theta. Cos 180 minus theta, it will become minus cos theta. Minus into minus, it will become plus. Understand? Now, from that you take the r square out. What is the remaining? You write here. And what is the next step? How you did it for to calculate 1 by r1? D is very less than r. What term I can neglect? D square by r square can be neglected. So, what happens? This d square by r square is neglected. This will become r square into 1 plus 2d cos theta by r. This is your r2 square. I want only r2. So, what happens? What you will do to find out r2? Take the square root. If we take the square root, r square will become r. And this term is 2d cos theta by r whole power r. So I want only 1 by R2. What is 1 by R2? 1 by R2 equal to 1 by R into 1 plus 2d cos theta by R whole power minus 1. Again, this term, that is 1 plus x whole power minus 1. This term I am going to expand using binomial expansion, and I will neglect the higher power since this value is very small. So what is 1 plus x whole power minus 1? If x is very small, I can neglect the term with higher power. So I will be getting 1 minus n. So I can write this as 1 by R2 equal to 1 by R into 1 plus, so it will become, what is n here? This is your n, that is R, 1 by 2. X is this value, 2d cos theta by R. 2 gets cancelled. The remaining is 1 by R2 is equal to 1 by R into 1 minus d cos theta by R. 1 minus d cos theta by R, equation 3. So I have calculated what is 1 by R1 and what is 1 by R2. What is the first equation? I am going to substitute these two, that is 1 by R1 and 1 by R2 in the first equation. What is the first equation we have written? B equal to 2 by 4 pi epsilon naught 1 by R1 minus 1 by R2. In this equation, we are going to substitute the values of R 1 by R1 and 1 by R2. We have calculated these two. Now just substitute 1 by R1 and 1 by R2 in this equation. So B will become 2 by 4 pi epsilon naught. In this 1 by R1 and 1 by R2. 1 by R is common, isn't it? So I can take it out because this term is common for both the values. This is 1 by R1 minus 1 by R2. Now we can write this 1 plus d cos theta by R. This is your 1 by R1 minus of 1 by R2. That is this value, 1 by R2. So I can also put this as simple bracket 1 minus d cos theta by R. Here, now you remove this bracket. This will become is equal to 2 by 4 pi epsilon naught R into 1 plus d cos theta by R minus into minus, this become, it is minus 1 minus into minus 2 d cos theta, it will become plus d cos theta by R. That is minus 1 plus 1 gets cancelled. Here d cos theta by R plus d cos theta by R. It will become 2d cos theta by R. So what happens to the electric potential? It is given by Q by 4 pi epsilon naught R into 2d cos theta by R. So this is your electric potential at any point due to your electric dipole. So at last we got this equation as Q in, what is this Q into 2d? This is nothing but your electric dipole moment, small letter p. Q into 2d is equal to a electric dipole moment. So I can write this electric potential as C cos theta by 4 pi epsilon naught R. So this will be your electric potential at any point. We didn't go on for if the point it is on its axial line or on its equatorial line. We have drawn this point at anywhere, but within the electric field. So this will be your electric potential at any point due to your electric dipole. Now we will go for on its axial line and on its equatorial line. The point P may be anywhere. It may be on its axial line or it may be on its equatorial line. We will go for the special cases. First one. This point, it may lie on its axial line at the side of plus q, isn't it? It also may lie the same axial line but on the side of minus q, because the dipole is like this, AB, here it is plus q, here it is minus q, the center, the point is here. The point may lie here also. If it lies here, it is on the side of plus q, but it is on the axial line. That is one condition. The point may lie here also. If it lies here, it is on the axial line, but it is on the side of minus q. These two are the one condition. It may also lie exactly on its equatorial line. Third one, if the point P lies on its equatorial line. In these three conditions, we will see what happens to the electric potential one by one. So, what are the three cases we can have? One, if the point P, if it lies on its axial line. See here, this is B and this is A, plus Q is here. We have drawn like this. This is theta and this is 180 minus theta, isn't it? If it lies here, starts from here and goes here, 0 to 180. If it is on the axial line at the side of plus q, what happens to theta? Theta is 0 degree. Here you substitute what is cos 0. What is cos 0? Cos 0 is 1. Then what happens to the potential? V equal to, what is the formula we got? V equal to P cos theta by 4 pi epsilon naught R. So now it will become, since cos 0 is 1, it will become P by 4 pi epsilon naught R. Here. Now, if the same point lies on the axial line, but it is at the side of minus q, what happens to theta? First, you have to find out what happens to this theta. Then you go for the equation. Theta, it will become 180 degree from here to here. Just came here to the plus q to minus q. Now theta is 180 degree. What is cos 180 degree? Then minus 1. So just substitute this in the formula. What happens to the electric potential? Minus P by 4 pi epsilon naught R. Now the same point, if it lies on its equatorial line, it is here. The point is here. What happens to the theta now? It is exactly at right angle. It will become 90 degree. So if it lies on its equatorial line, theta is 90. What is cos 90? It is 0. So what happens to the potential? If the point lies on its equatorial line, it is 0. So it will be having 0 potential when the point lies on its equatorial line. If it lies on its axial line at the side of minus q, it is minus p by 4 pi epsilon naught R. If it lies on its axial line at the side of plus q, it is p by 4 pi epsilon naught R. So it's an important 10 mark question. It's a very important 10 mark question. No need to write all the steps for calculating 1 by R1 and 1 by R2. Just to understand how you got the 1 by R1 and 1 by R2, you can write, but all the steps you should note down for your understanding. So don't skip any one step. All these are very, very important. When they ask this 10 mark question, you have to write all the special cases also. It is understood. Don't stop only up to the formula V equal to P cos theta by 4 pi epsilon naught R. You have to write all these special cases also. But this is very important. Yeah, it's important 10 mark question.